So, hello people, a very good morning to you all. This is Yashas from Team Galacticos, and today we are going to present about our rocket which we had designed in this 4 weeks. So, we have 7 team members: Yashas, which is me, Raj, Bhuvan, Shagun, Shanwant, Arjun, and Aditya. And we have segregated the rocketry teams to four like propulsion team, design team, recovery team, and electronics team. So in propulsion team we have Yashas, Raj, Bhuvan, Shanwant, and Arjun. And in the design team we have Raj, Bhuvan, Shagun, and Aditya. And in electronics team, we have Aditya, Shanwant, and Shagun. And finally, in the recovery team, we have Yashas, Raj, Bhuvan, Shanwant, and Arjun. So the content of our PPT is this: introduction, mission statement, propulsion, motor design, rocket design, electronics, recovery, the result and conclusion, the future, and last but not the least, acknowledgement. So, our plan is to design a rocket which is designed to reach an altitude between 10 to 15 kilometers, but now it has been changed to 30 kilometers because of the collection of more data about our rocket, carrying a payload of 2 kgs, which consists of weather, temperature, and storm detection equipment. So I would like to have propulsion team to explain about the propulsion of our rocket.
So for the propellant, we have decided to go with solid fuel as it can provide high thrust for relatively low cost and has simpler design. And the propellant is ammonium perchlorate based with HTPV aluminum, as it has high specific impulse, predictable and reproducible burning rate with ignition characteristic, and has high density. HTPV is considered to be a superior binder to achieve high combustion performance as well as desired propellant's physical and mechanical properties. With the ratio chosen is around 25% oxidizer and around 10% binder with 7.5% fuel with 4.5% IDP and 2.17% other components. So for the motor design, we designed using open motor software. So its dimension are given. A throat diameter of the nozzle, which is around 0.05 meter. The exit diameter is 0.15 meter. And the entire length of our motor is 1.1 meter, the diameter of about 0.15 meter. And also with the convergence and divergence angle of 30 and 15 degrees.
So we have decided on a star grain configuration for our motor, as it increases the burn area without sacrificing the amount of propellant carried and the volumetric efficiency. If the volumetric efficiency lowers, then it would lead to a lower ISP and a heavier motor. The point length of our grain is 0.07 meters and the point width is 0.035 meters. This was decided upon in order to keep the port to throat ratio between 2 to 3 and to keep the mass flux beneath 2. If the mass flux is above 2, then erosive burning could occur. So we have designed a P-class motor, which means that the total impulse is above 40,960 Newton seconds. Our ISP is 203. We had decided that our ISP should be around 200 in order to reduce the propellant consumption rate. Our peak pressure is 965 psi. Our peak Kn is 434.4. The Kn affects the burning characteristics of the propellant. However, our Kn is below the propellant's max range. The burn time of our motor is 4.4 seconds. And we had decided in initial calculations that in order to reach our required altitude, we needed an average thrust of around 10,000 units.
So now I would like to have a design team for explaining about the rocket design.
So We have decided to use trapezoidal fins as they give a good aerodynamic structure for our rocket. We decided to provide 3 fins because it gives a better stability compared to 4 fins. And when we provide these 3 fins to our rocket, the distance between center of pressure and the center of gravity was 1.81 calibers, which makes our rocket stable, and this increases the apogee of the rocket. Now, you might be wondering what this caliber is. The caliber is the unit of length which shows the distance between the center of pressure and the center of gravity. For the rocket to be stable, the distance between both of them should be around 1 caliber. If the distance between both of them is more than 5 caliber, then the rocket is quite unstable. So, coming to nose cone design, when we were designing the nose cone, there were 3 options available to us. First was the ogive. It has an arc at the top, and its rounded edges provide a good aerodynamic characteristics to our rocket. And also, it can be smoothly fitted into the body contour, thereby creating no break lines between the nose cone design and the cylindrical body. Coming to the conical nose cone design, as you could see in the picture, it resembles like a triangle. Its sharp edges makes it unsuitable for any rocket above 1 kilometer, and it produces more drags as compared to both of the nose cone design. Coming to elliptical nose cone design. This nose cone design is used in subsonic flights like the model rockets because it have a good aerodynamic performance at low speeds.
Hello everyone, my name is Aditya and today I'm going to be telling you about our material, dimensions and our rocket stability. A rocket has a rough length of around 1.73 meters and has a diameter of 0.155 meters. A rocket has a mass of around 43.5 kgs, and once the propellant is depleted and the parachutes are deployed, the weight will come down to around 20 kgs. For the nose cone and fins, we chose the titanium alloy, which has a density of around 4.43 grams per cubic meter, as our nose cone will be enduring high speed and high heat, and to get a lighter body, we chose a carbon fiber which has a density of 1.78 grams per cubic meter. Simulations and collected data. A rocket has a max speed of 1150 meters per second, or Mach 3.5, and the rocket will reach a apogee of around 30.931 kilometers as shown in the graph, and will also reach a maximum acceleration of 543 meters per second.
In our electronical payload, we have 2 things. First thing is the radio sound, and the second is the 2 cameras with inbuilt batteries. Now, you would be wondering that what is radio sound? The radio sound is a sensor which can calculate or measure all the weather elements like the air pressure, altitude, temperature, humidity, and wind speed and its direction. And it can also detect the storm by calculating or measuring all the weather elements. It has a reusable battery and has a radio transmitter for a ground receiver.
So now we would have recovery team to explain about the recovery of our rocket.
So the number of shroud lines of our parachute is going to be 6. The length of each shroud lines is going to be 0.3 meters. The density of it is going to be 1.6 gram per centimeter cube. And so the material we're going to use for our shroud lines is called elastic cord. So what is an elastic cord? An elastic cord is also known as a bungee cord and shock cord. Usually the elastic material is rubber and is bound by a fabric sheath. As it is elastic in nature, the bungee cord is used in a wide range of applications. It is commonly used to tie down the luggage on the outside of the vehicle. In our case, we are going to use this material for the shroud lines of our parachute. So the diameter of a parachute is going to be 6.5 meters. Our drag coefficient is 0.80. The density of our material is going to be 67 gram per centimeter cube. The material we're going to use for our parachute is going to be called as ripstop nylon. So what is ripstop nylon? Ripstop nylon are waterproof, water resistant, fire resistant, tear resistant with zero porosity. Note this down that it will not allow water or air through. Textures range from a soft and silk-like material to a crisp or stiff fabric. It has a favorable strength to weight ratio.
So now I'll be explaining about the parachute deployment and descent simulations. So our parachute will deploy at an altitude of 30 kilometers. The mass of our rocket after all the propellant is burned will be 22 kgs with a diameter of 6.5 meters, and the grounded velocity of the rocket will be 3.33 meters per second. With this, the total time from the liftoff till the recovery of our rocket will be 1 hour.
So we have successfully designed a rocket which can reach 30.9 kilometers, and we have collected the simulated data from Open Motor and Open Rocket. So our rocket uses AP/HTPV/AL propellant, and our motor can produce 10,000 newtons of thrust and has an ISP of 203. So the payload consists of a radio sound and two cameras, which have the capability to both check atmospheric conditions and warn incoming storm. In addition, the data can directly be transmitted to a ground receiver in case the recovery fails. So our recovery system consists of a parachute whose diameter is 6.5 meters, and this results in a ground hit velocity of 3.3 meters per second.
Now it's time to make our dream a reality. In future, we want to construct a working prototype of this rocket. We also intend to design rocket which can reach 100 kilometers and study additional data.
These are a few experiences we had taken during this cohort, and overall our experience in this SSERD program was fabulous, and I loved this program, and I'm looking forward to join other programs conducted by SSERD, and I like this program a lot. So we all would like to thank our mentors Nikita, Pratik, Sujay, Tejas, Aditya, Niharika, Aditi, and our supervisor Grishman, who conducted training sessions which had helped us a lot in our project. So thank you everyone. I hope you all enjoyed our presentation. Now I would like to open the floor for questions.
Thank you, team. We indeed enjoyed the presentation. So, as you said, let's open the floor for questions. Do we have anyone who would like to start off? Yeah, I see astronaut Harish raising hand. Please go ahead.
So I have a very small doubt. Are you planning to reuse it? And if you plan, are you going to refurbish it?
Yes, we are planning to reuse the rocket, and the frame and the motor is totally reusable, and we will fit it with new propellant, and if any part is damaged, then we will replace that before the next launch.
Okay, thank you.
Thank you, Harish. Do we have any other questions? Yes, Arun. Go ahead.
Thank you. Another lovely presentation. So I just wanted to know, what software did you use? Did you use any particular software to design your rocket?
Yes, sir. We used Open Rocket software.
Okay.
And to design our motor, we use Open Motor software.
Okay. Thank you. Lovely presentation.
Thank you so much, sir.
Right. Thank you, Arun. Any other questions from anyone? we can take one more question. Okay, perfect. Looks like we don't have any questions for.
I don't have a question, but a comment. I
Please,
think,
please, go ahead.
it's a very good presentation, and I think the young chops has done a fantastic effort even after the school hour, and it's amazing to see their interest and their involvement. Hopefully, look forward to see such engagement with these kids, and build their career towards research and innovations. Thank you.
Thank you so much, sir.